Now we're going to begin our discussion on electricity. And to start that off, we need to describe what electric charges are. So electric charges are pretty easy to understand if we do a quick demonstration here. So I have a piece of PVC pipe and just a regular old paper towel. And I'm just going to hit the PVC pipe on the paper towel. I could rub it on the paper towel too. You can actually hear a little bit of crackling as I'm doing this. That crackle is the transfer of charge from the paper to the PVC pipe. So if I do this, you can see, notice how the tinfoil jumped right initially there? Well, what was happening is I transferred some of that extra charge from the PVC pipe onto that tinfoil. And now we can see that since they both have that same type of charge, the PVC pipe is repelling that tinfoil. Try it one more time. You can see as soon as they touch, they become repulsive. I can do a similar experiment with a glass rod and some silk here. I'm just going to rub that silk on the glass rod. And you can see in this case, the charge that used to be repelled, it's a little bit weaker in this case, but the charge that used to be repelled from there is now attracted to the glass rod. Well, that tells me I have to have a different type of charge on the glass rod than I did on my PVC pipe. The PVC pipe repels the tinfoil, and the glass rod attracts it. Those are fundamentally different effects. So what's going on here? Well, when I first put the PVC pipe in contact with the paper towel, we transferred some charge. We also transferred some charge to the glass rod. For the sake of simplicity, we're just going to give, since we have these two types of charge, I'm going to call the charge on the PVC pipe negative. And I'm going to call the charge on the glass rod positive. Now, it turns out there's not really a good way to tell which one's positive or negative. There's nothing particularly positive-y about the type of charge on the PVC pipe, or particularly negative-y for that matter. It's just a label that we put on it. Since we have two types, we also have positives and negatives. We're just going to call it positive and negatives as a label. So here's what's happening. Got my negatively charged PVC pipe. We put that in contact with our tinfoil. It's going to transfer some of its negative charge onto that tinfoil. And that tinfoil is going to be repelled by the negative PVC pipe. So why was it attracted when we did the same experiment with the glass and the silk? Well, in the case of the glass, it turns out it was getting a different type of charge, which I will label with a plus sign to represent that different type of charge on the glass. And when a plus charge sees a negative charge, it turns out it feels a force in the opposite direction. So when my glass was brought near my negatively charged tinfoil, it was attracted. It felt a force pulling those two types of charges together. So what we can say about this is, given the two types of charges we've discovered, there are really three types of interactions. I could have two positive charges brought together. In that case, they would repel each other. I could have a positive and a negative type of charge brought together, and they would attract each other. And although we didn't do this experiment, it's easy enough to do. You could just take the glass and look at it. In both cases, we'll get positives repelling and negatives repelling. Whether if they're like charges, they're going to repel each other. This summarizes all the different interactions we can have electrostatically. Like charges repel, opposite charges attract. Now, as best we can tell, there is no third type of charge. So we're pretty good with that plus and minus label because there's only two types of charges. If there was a third type of charge, maybe we need to come up with a different label. Red, green, blue instead of plus minus. But as best we can tell, there is no third type of charge, so we're good just labeling them as plus minus. And again, the positive and negative labels don't really mean anything particularly special. It's just a label that we put on the charge. So there's nothing particularly positive-y about positive charges. There's nothing particularly negative-y about negative charges. If you look at a microscope, under a microscope, you don't see little plus signs on the positive charges and minus signs on the negative charges. It's just, again, just a label that we're using. Toward that end, it's also kind of a bad label in a certain respect. And Ben Franklin, I believe, gets the blame for this from a lot of physicists. So it turns out that protons, we know, are positively charged, and electrons are negatively charged. And when we talk about electric current, you'll see that it's actually the electrons that are the charges that are flowing. Which makes it difficult because you have to talk about the flow of negative charges rather than positive charges. And it kind of makes the math a little bit weird because current is defined as the flow of positive charge. We'll talk about that more in a bit, but for now, what you want to remember is that there's two types of charges, one positive, one negative, and that like charges repel and opposite charges attract. Most matter that we interact with is composed of protons and electrons. Protons and electrons go to make up atoms, and atoms go turn into molecules, which turn into the everyday substances we interact with. So if matter is made of protons and protons are positively charged and electrons are negatively charged, why is it that we don't see this strange attraction everywhere that we had with the PVC pipe and the tinfoil? Well, the reason is the electrostatic force is very, very strong. And for that reason, the electric forces tend to cancel each other out because we tend to get an equal number of an equal amount of positive charges and an equal amount of negative charges. And you can see this in atomic structure. Suppose we take hydrogen atom. A hydrogen atom has a nucleus that's composed of a positive charge, the proton. On the outside, it has an electron in some orbital. And if I look at the charges of those objects, it turns out that the electron has exactly the same amount of charge, but with an opposite sign. So an electron has negative 1.6 times 10 to the minus 19 coulombs of charge. So coulomb is the unit of charge that we're going to be working with here. It's just a measure of how much charge we have. And the charge of the proton is the same thing, but just positive. So it's positive 1.6 times 10 to the minus 19 coulombs. What happens as charges move around? Well, it turns out we have a name for that. That's just called electric current. And we define electric current as the flow of electric charge, specifically the flow of positive electric charge. So suppose, how do we actually measure what current is? What does that actually mean, the flow of positive charge? Well, suppose, just as an analogy, you're sitting over here on the side of a road and you're watching cars go by. Well, here's a car, it just goes by. And let's say you watch for a minute and you count the number of cars that go by in a minute. Yes. For example, maybe you have 33 cars go by in 1 minute. Well, the same thing is going to be true. You're going to do exactly the same thing to compute electric current, except the only difference is, instead of looking at cars go by, you're going to look at the number of charges that go by. So, suppose you're watching what's going on, and you see some positive charge come past you. Suppose there's 33 coulombs of positive charge. Well, you would say that the current, which we will call I, is going to be given by 33 coulombs of charge in 1 second. So that'd be 33 coulombs per second. So all we're doing when we're computing the current is we're just counting how many charges go by each second. if we want to write a mathematical formula for the current, we would say that the current, again given by the symbol I, is equal to how much charge passes by in some unit time, and the units of that would be coulombs per second. But we also have a shorthand for that unit. We have the shorthand A, which stands for amperes. So we can measure the current of passing through an electrical circuit in amps or amperes. Now, suppose I take some piece of metal, maybe it's in a dumbbell shape, and I hook it up to a battery in such a way. Let's suppose for the moment that the positive charges in that metal were flowing to the right. Okay, so we've got positive charges flowing to the right. Well, what's going to happen is those positive charges would start to build up on the right because they couldn't go any further. And they would be leaving behind, since it started off neutral, if I take positive charges away from the left, I've got to leave negative charges behind on the left. So we would end up with the right plate being positively charged, the left plate being negatively charged. Let's consider a different situation. Suppose I have negative charges in my dumbbell, but now they're moving to the left. Well, just as before, those negative charges would hit the wall, and they would start to build up on the left, but they would have left positive charges behind on the right. And I should be careful here. I should really put an equal number of positive and negative charges on either side, because in total we have to add up to 0 net charge, because the object was initially neutral. But what we can see from this is that there's no way to really tell from this picture, by the time all my charges are finished flowing, what's happened. I can't tell whether it's positive charges moved to the right or negative charges moved to the left, because either way I end up with positive charges on the right and negative charges on the left. So functionally, on a macroscopic scale, which we humans live at, there's no way to tell which one is actually moving. How do we tell on a microscopic scale? Well, it turns out that if you measure the mass of a proton, compare that to the mass of an electron, we know the proton is 2,000 times heavier, about 2,000 times heavier than the mass of the electron. So if I were to push on both of those charges, what we could say is that the electron is going to be accelerated much more. It's going to be moving much faster if we hit it with the same force. The reason being because it's a lot smaller. If it's 2,000 times smaller, it's going to be a lot easier to accelerate. So we can imagine that the flow of charges is really, in a metal, is really the electrons that are flowing. Practically, it doesn't make a difference, and since we started calling current the flow of positive charges, we imagine it as positive charges that are moving, rather than negative charges moving in the opposite direction. We just define it as the flow of positive charge. So it's really this picture, but we're going to imagine it being like this picture when we're dealing with circuits. We're just going to pretend that it's really the positive charges flowing, just because that conceptually makes it easier to think about. But know that it's really this going on. The electrons, which are much tinier, are the